Welcome friends, I am Tanmay. In this video, we'll discuss about a question which came in CSIR-NET 2013. It's a 2 marks question. So, okay. And welcome to my channel. This chemistry, the mystery of molecules where I explain this different chemistry related problems and basic understanding about chemistry. So let's go to the question. So I suggest you read question carefully. It is essential. So the question is, among the following compounds, which one have lowest energy barrier for the cis-trans isomerization? So the most important point, lowest energy barrier and for cis-trans isomerization, these 2 points. I always tell you that try to realize what actually asking in the question. Maybe what is written, it is a mask or hidden. The actual answer is hidden here also. Actually, see, it's a 2 marks question, but if you don't found the trick, okay, it will look a big question, and you must be careful while spending more time on a 2 marks question, because if you can't attempt the 4 mark question properly, then that is not profitable for you. So you see, among the following the compound which has lowest energy or barrier for cis-trans isomerization. So now you have to know what they are actually asking. See, every compound is conjugated planar and conjugated planar and contains some number of electron. So first question, this should be related to aromaticity. Okay, first point. Second point, they are asking lowest energy barrier for cis-trans isomerization. Cis-trans, what we have learned, is a double bond with respect to double bond, means R1 and R2. This is cis, and if it goes, what happens? This is trans. R1, R2. Sorry, this is R2, this is R1. And how this happens? Actually, double bonds don't allow the rotation of this, so it must be a single bond in order to rotate. Okay? Keep this thing in mind. This double bond don't allow the rotation, but single bond allows, so this goes through a single bond. Carbon-carbon single bond. Because if we consider carbon, it is free to rotate. So the question is, this is all our sp2. Why rotation? What they want to know this part. You see, this trans, this trans, this trans, this trans. So trans with respect to what? Trans with respect to this double bond. So actual what the examiner is asking to you, the question is, in which case this bond will rotate, and rotate how? Through, actually rotation happens through a single bond, because triple bond is not rotate like that. Actually triple bond is different. Okay, so we'll discuss in some another example. So actually this double bond rotation on a double bond is not possible. It should be single bond. So the question, in which case, actual question is, in which case this bond have maximum single bond character. So this is the actual question. This is the actual question asked, but different way. The student get confused and they end up with mistake and they waste their time. So be calm and cool and try. Which one will have maximum single bond character? Okay. So we know this is cyclic, planar, conjugated. So aromaticity, according to Huckel rule, cyclic, planar and conjugated with 4n plus 2 number of pi electron is aromatic arrow, and 4n number of pi electron is anti-arrow. Keep this thing in mind. This question is related to Huckel rules of aromaticity. Okay. This question you can see. Here you can see that this double bond will be in resonance or double bond will be in delocalization in this two bond. So what will happen if it is in resonance? So if double bond goes this side, so the product will look like, double bond goes to this side, means this side, so it will contain this and this, and this is this Ame versus this is Ame, this is cation. So this is anti-arrow. Right now anti-aromatic 4 pi electron, and this is arrow. If we consider the reverse one, means plus charge is here and negative charge is here. How? This double bond is delocalized in this way. Then here we will have 8 pi electron and here 2 pi electron. Now this is arrow, this is anti-arrow. So in both, so the conclusion of the story, in both sides, one part is stabilization and another is unstabilization. Okay, keep this thing in mind. So its contribution is expected that this and this bond will not have that much tendency to delocalize, because delocalization is charge distribution. Charge distribution creates unstabilization, and if charge distribution will happen that time when this unstabilization will be balanced by some stabilization factor. I'll explain how stabilization is coming. So okay, keep this thing in mind. If it is a symmetrical molecule, both sides same. So if it delocalizes in this way, the ultimate product will look, the canonical form will look like, these all are canonical forms, will look like this. So this is come, it's negative, this is positive, this is stabilization, this is unstabilization, similar like this. So one part is stable, one part is unstable, and this is a symmetrical molecule, so both case same. Okay, let's come to this point. This point is, if we draw the canonical form, this. So if bond goes in this direction, what will be the consequence? Negative charge will be here, this positive charge will be here, this contains 6 pi electron, arrow means aromatic stabilized. This is contains also 6 pi electron, so this is also aromatic stabilized arrow. If we check the another option, this, so what will be the consequence? Sorry, single bond. So plus charge here, minus charge here. So here 8 pi electron, anti-arrow. Here also 4 pi electron, anti-arrow. So this way delocalization will not happen. So let's eliminate. Let's consider about this canonical form, where both are stable. This is also stable, this is also stable. Now let's consider. This is similar like this, symmetrical structure, so we will draw only one. If this side, what will happen? So one is negative and one is positive. So one side positive means 6 pi electron, arrow, so stable. This is 8 pi electron, anti-arrow, so unstable. Okay. So what is our achievement? This is one part is stable, one part is unstable. So if we make a table, if we consider A, B, C and D, it will be helpful for you. Let's make a table. A, B, C and D. This is the table. So A is stable to and unstable. A is S, ST and UST. ST for stable, UST unstable. B is one part stable, one part unstable. So ST versus UST. C stable, stable. ST versus ST. D ST or UST. UST means unstable, ST means stable. Or this could be reverse. Means what I mean that one part is stable, one part unstable. So in case of A, 1 unit stabilization, 1 unit unstable. So net this. Net almost nothing. This is. So only one case both sides stabilization possible. That is C. Okay. So in this way, actually this problem is not difficult. You have to understand this stable, unstable. This part, if you can understand directly, you don't need to spend more time. You can go to the problem directly. So let's discuss about this problem only. I'll clean up other part because C, only I shall keep C because it will create confusion. Let's clean. So from discussion we know that C conformer is stable and stable. What will be the actual form look like? This is positive, this is negative. In this way, both rings are stabilized, means charge separation creates unstabilization. I have explained many times. But here, charge separation is creating stabilization, and that is aromatic stabilization. Aromatic stabilization is a huge stabilization. So this and this is the methyl group. Okay. So due to this aromatic stabilization, this bond, this in between bond will prefer to have some more single bond character compared to others. Okay. So this has maximum single bond character. Maximum single bond character. Okay, compared to others or among ABCD. So maximum single bond means I told that single bond rotation possible, but double bond rotation not possible. So here rotation will be maximum possible among 4. So this is maximum rotation possible in case of this example. Okay. So rotation possible. So rotation among 4 easily possible means corresponding energy barrier for cis-trans. Cis-trans will be less. Okay, this energy barrier will be less here. Easily it has more single bond character, so it can rotate easily. Means two ring can rotate easily. So it will have minimum energy barrier for this rotation. So I guess, so this is the formal discussion. So how to solve this trick? First, when you see all the questions, this question you have to find out what actually they are asking. What they are actually asking, maximum single bond character. So if you can find out this thing, 50% problem you have solved. Second part, how this single bond is coming through delocalization in the rings. Now you delocalize, this is 4, this is 6. Another thing, so you make a table, ST-UST. In this way, just think about the canonical forms. Don't need to write on the paper, it will take time. Think in mind and make a table. In this way, you will end up that, okay, this form. And when you got answer for someone, you have to cross check again that for correct one, that it is right or wrong. Okay, ST. Okay, now think about that. Okay, this is an azulene derivative. Means one part is 5 member contains 6 electron, this is 7 electron. That is stable. So this charge separation will create aromatic stabilization. That means this bond will be single, so rotation will be possible. So compared to this 4, among these 4, this has lowest energy for CC bond rotation. That means maximum single bond character. Okay. So this is the end of my video. So thank you everyone for listening this video. If you like my videos, please give a thumbs up and share this video with your friends, and subscribe my channel Chemistry the Mystery of Molecules, and please press the bell icon to get notification about every single video I upload. So bye, see you in my next video.